In this presentation, we'll briefly describe the fifth experiment, measurement of pH, where it should be obvious in this experiment, we'll find ourselves measuring the pH of various solutions using a number of indicators and a pH probe. That's right, people, a pH probe. Can you imagine? That said, in addition to measuring pH, we'll find ourselves comparing the acidity of some of these solutions and further examining other solutions with respect to further addition of both acid and base. Seriously, this experiment is a total score, which will have you screaming, "Chemistry is awesome," upon its conclusion. So, moving forward, as you probably already know, acids are sour, bases are bitter. And we're going to use this information to get through this experiment by tasting everything. Seriously, that's crazy, right? You wouldn't want to do that. Never mind the fact that history has proven, well, if anything, history has demonstrated that a lot of cool chemicals have been discovered by random chance. For instance, there's this chemical known as cyclamate. It's one of the first artificial sweeteners. Apparently, it was discovered by chance when the chemist working with it put his cigarette, because, back in 1937, people smoked cigarettes in the lab, put a cigarette down on the bench top, then picked it back up again for another drag and found it to be sweet. And obviously, it must have been due to the chemical he's working with. And then, of course, aspartame, discovered as another artificial sweetener in the 60s, discovered when the chemist working with it went to lick his finger before turning the page in the notebook. And then, of course, found his finger to be sweet. Just love these chance discoveries. One of my favorites, lysergic acid diethylamide, known as LSD, or if you will, just acid, discovered when the person who synthesized it, Hoffman, allowed a drop to fall accidentally into his skin. The acid absorbed through his skin, and Hoffman went on essentially his first trip. Of many, I imagine. Anyhow, back to it. We don't want to come in contact with the chemicals we work with. And so I'm got on my screen here this idea that we're going to taste the chemicals. That is totally crazy. Rather than taste the chemicals, we're going to rely on a variety of techniques to measure the pH. The first of which will be litmus paper. Litmus is nothing more than paper that contains a dye that changes color according to pH. Red litmus paper will turn blue under basic conditions. The blue paper will turn red under acidic conditions. And although I'm saying blue and red, recognize the actual colors are more like purple and pink. Go figure. The red paper, which looks somewhat pink, will turn a purplish blue upon exposure to a base. And the purplish blue paper will turn a reddish pink upon exposure to an acid. Moving forward, litmus paper works because it contains what's known as an indicator. Indicators are simply organic compounds that undergo structural changes with adjustments to pH. And that structural change will give rise to a change in the color of the solution. It's a real simple idea, but goes super far. One type of indicator, known as universal indicator, is actually a mixture of 3 or 4 indicators that allows for essentially a change from reds to blues over the common pH range. That is, let's say 1 to 14. If we take that universal indicator and add it to paper, we have what's known as pH paper. pH paper, which contains a mixture of indicators, will change color according to the pH of the solution into which it's placed. We generally think of the acidic region as being more red and the blues for basic. It's a simple idea. You take a strip of paper, which is exposed to the indicators. You dip it into the solution. The paper changes color according to the pH. You then hold that strip of paper up against the chart as a way of measuring pH. And in case you're wondering, yes, those are my hands. A pH probe, which will be used in this experiment, is nothing more than a device which allows us to measure pH directly. We'll talk much more about the pH probe later in the semester, but for the moment, let's keep it simple. This device will measure the potential difference between two electrodes, where this voltage, or potential difference, depends on the concentration of the hydronium ion. And therefore, this device will allow for the direct measurement of the solution's acidity. That is a direct measurement of the solution pH. There are three parts to this experiment. In the first part of the experiment, you'll find yourself measuring the pH of common household materials. You'll find yourself beginning this part of the experiment by constructing a well plate. That is, you'll have a plastic plate that consists of 24 wells to which you're going to add various solutions. Column 1, glass cleaner. That is a solution of ammonia. Column 2, baking soda. That is your sodium bicarbonate. A soap solution in column 3. Your acidic lemon juice in column 4, milk to column 5, and everyone's favorite, 7, up to column 6. You'll then test the pH of these solutions using a variety of techniques. You'll add pH paper to row A, litmus paper in rows B and C. You'll then use a pH probe to test the pH directly across row D. And then, as if this weren't fun enough, you're going to add indicator solutions dimethyl blue to row A, methyl orange across row B, methyl red across row C, and bromothymol blue across row D. Where these four indicators will change color according to pH. For instance, bromothymol blue, for pH values 6 and lower, it's yellow. For 7.6 and above, it's blue. Between 6 and 7.6, it's somewhere between yellow and blue, maybe green. Upon adding these four indicators, you'll have an incredibly colorful well plate to examine. In part 2 of the experiment, we'll repeat the procedures of part 1 using, instead of household materials, chemicals that are more common to the chemistry lab. Hydrochloric acid across column 1, sodium hydroxide across column 2. Column 3 will contain the acidic ammonium chloride, and column 4 will contain the basic sodium formate. And then we'll have water, that is deionized water, across column 5. As before in part 1, we'll use pH paper, red and blue litmus paper as a way of assessing the acidity across rows A through C. We'll then make a direct measurement of pH using a pH probe on row D. And as before, we'll then add indicators, thymol blue, methyl orange, methyl red, and bromothymol blue across the rows. As in part 1, with part 2, you'll find yourself recording both colors and, where appropriate, a pH value. In the third and final part of the experiment, you're going to examine the resistance to pH change. I know, you heard me say resistance to pH change, but all you can think is buffer. One thing we've learned, God, I hope it's at least this one thing we've learned, Buffers resist changes to pH. Here you'll be using the same well plate as before, but instead of all the wells, obviously a smaller number. You'll add to column 1 deionized water, formic acid to column 2, sodium formate to column 3, and the formate buffer, a mixture of formic acid and sodium formate, to column 4. You'll then measure the pH across row A. You'll add a drop of 0.1 molar hydrochloric acid across row B and measure the new pH. You'll then add a drop of 0.1 molar sodium hydroxide across row C and measure its pH. Where we would expect to see, and this experiment is finished, a resistance to pH change across column 4 and a lack of resistance across column 1. I hope you enjoy this experiment. Of course, I say hope we enjoyed the experiment. You can turn that W upside down to make an M. It'll be all about me doing the experiment, and you get to enjoy it on the video, which we'll post for you at some point in the future. Take care, have fun.